Hello, we're going to talk about section 3.1 today. Let's get started. We're talking about introduction to probability. So things to take notes on for this section would be what is a random event, and then what are disjoint or mutually exclusive events, and what is the general addition rule, and then what's the difference between a probability distribution and a sample space, and then also complementary events, and also independent and dependent events, and finally multiplication rule for independent events. Okay, so a random process. A random process is a situation in which we know what outcomes could happen, but we don't know which particular outcome will happen. So for instance, you've got a coin toss, you know that it's going to be heads or tails, but you don't know exactly which one. So it's often helpful to model a random process, even if it's not truly random. All right. Then as a quick, if you're really interested, there's a little link there to see like how iTunes chooses random songs. All right. There are several possible interpretations of probability, but they almost completely agree on the mathematical rules probability must follow. So we're gonna, like, the mathematical notation is thinking of capital P as a function. And so I put in the event A and I get out a probability that's between 0 and 1. Okay. So then there's two different interpretations of this. One of them is the frequentist, which says the probability of an outcome is the proportion of times the outcome would occur if we observe the random process an infinite number of times. Okay. And then there's the Bayesian interpretation. So these are really different philosophies of statistics. So a Bayesian interpretation interprets probability as a subjective degree of belief. The same event, two separate people could have different viewpoints and so assign different probabilities. This is largely popularized by revolutionary advance in computational technology methods during the last 20 years. And so it turns out when you try to do more teaching machines things like artificial intelligence and stuff, Bayesian has been better than frequentist in terms of statistics. So it's a lot more common these days. So I've got a little comic for you. So I can't see this. Let's move that. Okay. Did the sun just explode? It's night, so we're not sure. And the person on the left says, this neutrino detector measures whether the sun has gone nova. The person on the right says, then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. Let's try. Detector, has the sun gone nova? Roll. Yes. So a frequentist statistician would say the probability of this result happening by chance is 1/36. Since that's less than 5% chance, I conclude the sun has exploded. And the Bayesian, who are known to be gamblers, says, bet you $50 it hasn't. All right. You might not get that, but if you knew more about Bayesian and frequentist statistics, you would. All right, moving on. Let's practice. Which of the following events would you be most surprised by? Getting exactly 3 heads in 10 coin flips, 3 heads in 100 coin flips, or 3 heads in 1,000 coin flips? And the answer is, of course, 3 heads in 1,000 coin flips. That would be really rare. Okay, so the law of large numbers, and that kind of relates to this. The law of large numbers states that more observations are collected, the proportion of occurrences with a particular outcome, I will put a little p hat, converges to the probability of that outcome, p. So p hat, whenever we put a hat over a variable, it means like the thing we're actually observing. And so it would get closer to the actual probability. So if you only do 1 head flip, it's 0 or 1, so you're not close to half. But if you do it 100 or 1,000 or 10,000 times, it gets closer and closer to 0.5. All right. When tossing a fair coin, if heads comes up on each of the first 10 tosses, what do you think the chances that another head will come up in the next toss? 0.5, less than 0.5, or more than 0.5? Okay. This is one of those trick questions. The answer is still 0.5 because I told you it was a fair coin. Now you might wonder if it comes up head that many times, like, is it a fair coin? But if you're sure it's a fair coin, then the probability is still 0.5. All right. And there's I think it's called the gambler's fallacy. And you might hear it in things like baseball. Like if someone is a good hitter and he's he's struck out several times, people might say, well, he's due. And that's not true. If he still has like roughly the same probability of hitting that he did when he missed those couple times. All right, so the idea of being due is not good statistics, not good use of probability theory. Common misunderstanding of the law of large numbers, LLN, is that random processes are supposed to compensate for whatever happens in the past. This is not true. So it's called the gambler's fallacy. So what are disjoint and non-disjoint outcomes? So disjoint, otherwise known as mutually exclusive, cannot happen at the same time. So the outcome of a single coin toss cannot be both heads and tails. A student both cannot fail and pass a class. A single card drawn from a deck cannot be an ace and a queen. So, but some things can be non-disjoint. So a student can get an A in stats and an A in econ in the same semester. Okay. So what is the probability of drawing a jack or a red card from the well-shuffled full deck? Well, those events are not mutually exclusive. So this is my link. So since they're not mutually exclusive, when you add the probabilities, you have to subtract the and part, all right? Because otherwise you're counting the red jacks twice if you add the probabilities. So we subtract the probability of jack and red to not double count. Make sense? So when events are disjoint, I can add the probabilities. When they're not disjoint, I add the probabilities and subtract the probability of both of them happening. Okay, so what is the probability that a randomly sampled student thinks marijuana should be legalized or they agree with their parents' political views? So we've got, they want to legalize MJ and they share parents' political views. So which formula gives us the correct answer? Is it A, B, C, or D? So let's look at A. A is 40 plus 36 minus 78. That is not correct because we want to do legalize or agree. So if we look at part B, then 114 is the total for the yes, and 118 is the total for the yes. And so 114, 118, and then subtract 78 because that's double counting. So we want to make sure we don't double count. So you subtract the 78 and then you divide by the total. So that is the correct answer. Okay, so that's going to get us to that principle we can write with a mathematical formula. And that is called the general addition rule. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So when things are disjoint, you can simplify it because you can't, disjoint events, mutually exclusive events, have zero probability for A and B. So you can drop that when things are mutually exclusive. But this formula works for all situations, okay? Okay, moving on. Probability distribution lists all possible events and the probabilities with which they occur. The probability distribution for the gender of one kid is now, I mean, if you did lab 1, you'll know it's not exactly 50%. It's more like 51% for male and 49% for female. But anyway, we'll just move with this. So the probability for getting one kid, 0.5. So the rules for probability distributions, the events are listed, must be disjoint. So that's, having a kid, they're going to be male or female. Okay. And then each probability must be between 0 and 1. And then the probabilities must total up to 1. Otherwise, it's not a probability distribution. Okay. So in the probability for having 2 kids, you could have male, male, female, female, oldest kid male, youngest kid female, or oldest kid female, youngest kid male. Okay. All right. In a survey, 52% of respondents said they are Democrats. What is the probability that a randomly selected respondent from the sample is Republican? Is it 0.48? Is it more than 0.48? Is it less than 0.48? Or cannot calculate using only the information given? Well, what do you think? I'll give you the answer in 3, 2, 1. The answer is D. I didn't give you enough information. So if there was only 2 political parties that anyone could be a part of, then it would be A. But there are third parties, there are independents, so it could be C. We know that B is not possible. Make sense? All right. Let's do a sample space and complements. A sample space is a collection of all possible outcomes of a trial. A couple is 1 kid. What is the sample space for the gender of the kid? So we like to call our sample spaces capital S. And we use curly brackets when we have a set of things. We're talking about things that we can count. So in this case, the sample space is male or female. So a couple has 2 kids. What is the sample space for the gender of these kids? Well, if you're keeping track of the order of the kids, then you have 4 possibilities, right? Male, male, female, 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 male, or male, female. Okay. Complementary events are 2 mutually exclusive events whose probabilities that add up to 1. So if a couple is 1 kid, if we know that the kid is not a boy, what is the gender of the kid? It's a girl, right? So the boy and girl are complementary events. A couple is 2 kids. If we know that they are not both girls, what are the possibilities? Well, then there's 3 other events it could be. Okay, so complementary events are things we can figure out from the sample space. Okay, so whenever you see the curly brackets, think about like I don't know. I've got young kids right now, and we're teaching them how to count. So imagine like those cardboard books that you learned how to count on, and there'd be pages like, here's 3 owls. How many owls are there? And here's 4 fish. How many fish are there? Whenever you see curly brackets, think like the number of things on a page of a counting book. All right, it's how we this idea of sets is like the foundation of mathematics and counting. So it's just a notation we use for really simple things. Okay, so don't freak out about curly brackets, just a new notation for something you've known since you were like 5. Okay, all right. Independence. 2 processes are independent if knowing the outcome of one provides no useful information about the outcome of the other. So if I tell you the coin landed on a head and on the first toss, you don't know what it's going to be like. It tells you no information about what the second toss will be. So outcomes of 2 coin tosses are independent. Now, knowing the first card drawn from the deck is an ace does provide useful information for drawing the next card, because it is less likely to be an ace. Okay. Drawing things from a deck or something else without replacement are dependent, whereas flipping a coin or drawing a card and then putting it back is independent. All right. Between January 9th through 12th, 2013, Survey USA interviewed a random sample of 500 North Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime or makes society more dangerous. 58% of all respondents said it protects citizens, 67% of white respondents, 28% of Black respondents, and 64% of Hispanic respondents shared this view. Which of the below is true? Opinion on gun ownership and race ethnicity are most likely A, complementary, B, mutually exclusive, C, independent, D, dependent, E, disjoint. Opinion on gun ownership and race and ethnicity are most likely which of those? All right, think about it. Try to come up with the answer in your head. I'm gonna give you the answer in 3, 2, 1. The answer is dependent because of people's views, because different races, the way people identify with race tells you something about how likely their opinion on gun ownership is. And so that makes it a dependent event. Okay, checking for independence. If P, so here's a probability. Probability of A occurs given that B is true. We write it with the line. So this is the notation for that. Okay, so whenever you see P of A line B, read it in your head, probability of A given B. All right, if probability of A given B is just equal to probability of A, then it's independent. Okay. So probability of answering guns protect citizens is 0.58, but probability of randomly selected resident saying gun ownership protect citizens given the resident is white, or probability to protect citizens given white is 0.67. Probability to protect citizens given black is 0.28. Probability to protect citizens given Hispanic is 0.64. So probability to protect citizens varies by race ethnicity. Therefore, opinion on gun ownership and race ethnicity are most likely dependent. All right, determining dependence based on sample data. If conditional probabilities calculated based on sample data suggest dependence between two variables, the next step is to conduct a hypothesis test to determine if the observed difference between the probabilities is likely or unlikely to have happened by chance, right? Because we didn't sample the entire state, we just had a small sample, all right? So if the observed difference between the conditional probabilities is large, then there's strong evidence the difference is real. If the sample is large, then even a small difference can provide a strong evidence for a real difference. Okay, so we saw that the difference is very big, but we weren't, under which condition would you be more convinced of real difference between the proportions of whites and Hispanics who think gun widespread, I don't think I said that right, gun ownership protects citizens. So remember that the white and Hispanic numbers were 0.67 and 0.64, which is a small difference. So if it's a small difference and it's 500 people, or a small difference in 50,000 people, which one is most likely to be able to show you that it's the difference is real and not just due to random chance? And the answer is the 50,000 sample. All right, now let's talk about the product rule. When things are independent, you can multiply the probabilities, okay? So remember back when we had mutually exclusive events, if we had an or, we could add the probabilities. And then we also had a general rule for adding anything. And then more generally, if we have a bunch of independent events, you can just multiply them, but only if they're independent, not in general. Okay, so if you get, you toss a coin twice, what is the probability of getting 2 tails in a row? It's probability of first, so 1/2 times 1/2 gives 1/4. Okay. So a recent Gallup poll suggests 25.5% of Texans do not have health insurance as of June 2012. Assuming the uninsured rate stayed constant, what is the probability that 2 randomly selected Texans are both uninsured? Okay, so you're sampling from a really big population. So which one is it? Is it 25.5 squared, 0.255 squared, 0.255 times 2, or 1 minus 0.255 squared? All right, think about it. Come up with the answer in your head. The answer is coming in 3, 2, 1. The answer is 0.255 squared. All right, because it's basically independent since the sample is so large. So then you can just square the probability. All right, disjoint versus complementary. So do the sum of probabilities of two disjoint events always add up to 1? Not necessarily. There may be more than 2 events. Okay, so like the political party affiliation. Okay, do the sum of probabilities of 2 complementary events always add up to 1? Yes, that's the definition of complementary events. Okay, so like heads and tails. All right, put everything together. If we were randomly select 5 Texans, what is the probability that at least one of them is uninsured? So we gotta look at our sample space, like 0, 1, 2, 3, 4, 5. Okay, we're interested in the highlighted ones. So basically not 0. Okay, so we can divide up the sample space into 2 categories, 0 and at least 1. We're doing this because it's more complicated to do like 2, 3, 4, and 5. So that's complementary. So we can look at probability of at least 1 is 1 minus probability of none. So 1 minus probability of none would be kind of the opposite of that. So 1 minus, and then that's an independent thing. So you take it to the 5th power, which means multiply it times itself 5 times, and you get 77. So 77% chance. Okay. All right. Moving on. So if 5% of Grace students are vegetarian or vegan, what is the probability that among a random sample of 3 Grace students, at least 1 is vegetarian or vegan? Okay. Think about this. Maybe pause the video and try to answer the question in your head. Okay. Sorry, I messed it up. Anyway, answers come in 3, 2, 1. So it's if it's 5% of students are vegetarian or vegan, and the chance of randomly sampling 3 students, at least 1 is vegetarian or vegan, is so P of at least 1 is 1 minus none, right? And so none would be like not being vegetarian or vegan. That's a 95% chance. So you cube that, 1 minus that. So that's it. All right, that completes this section.